In this video, we will discuss about capacitor behavior in DC. First, let's see the behavior of capacitor while charging. Let us consider, initially, capacitor plates are uncharged, that is, no charge exists on the plates, it means, no voltage across the capacitor. When a capacitor is connected across a battery, through a switch, such that, positive end of the battery to plate 1, and negative end of the battery to plate 2. Suppose, the switch is closed at time, t1. There will be a closed path, and electrons start rushing into plate 2 of the capacitor, from the negative end of the battery. At this moment, the current will be high. As the electrons start accumulating on plate 2, it will be negatively charged. As plate 1 doesn't have electrons on it, it is said to be positively charged, with respect to plate 2. So, voltage build at capacitor starts after time, t1. Hence it is clear that voltage starts rising, from 0 magnitude, after time, t1. Now, let's observe, between time, t1, and t2. As the voltage build at capacitor starts after time, t1. The potential difference, between battery, and capacitor plates, reduces. That oppose, the huge charge coming from negative end of the battery. It indicates, capacitor is opposing the instantaneous change in voltage, across it. After time t2, the same process will continue. So the charges will gradually accumulate on plate 2, until the capacitor is fully charged. When the capacitor is fully charged, it attains the same voltage as the battery. The time taken to fully charge the capacitor is called charging time of capacitor. As there is no potential difference between battery and capacitor, no charge will flow, that is, capacitor acts as an open circuit. Hence, we can say that, for DC, the capacitor has infinite opposition, in steady state. And thus, the capacitor blocks DC current. Now, let's see, the electric field, and energy storage in capacitor. Due to the potential difference between the capacitor plates, there is a strong force of attraction, between the plates. But the electrons can't travel from plate 2, to plate 1, through the dielectric medium, or insulator. So, an electric field, is developed, between the plates. We can say that, the energy is stored, in the form of electric field. Now, let's see, what exactly happens, when we just disconnect the capacitor. When we disconnect the capacitor from the battery, the charge accumulated on the plates of capacitor can't escape, as there is no path for the electrons to flow. As the charge exists on the plates, even after the removal of battery, a capacitor is said to be storing the energy, in the form of electric field. Now, let's see, discharging of capacitor. Let us now connect the capacitor to a light bulb. At that instant, due to the potential of capacitor, a huge amount of charges try to flow from capacitor's negative end to the positive end, and the bulb starts glowing. As the charges move away from negative end of capacitor, the potential across capacitor starts decaying. As the potential reduces, less number of charges will flow from capacitor to bulb. It indicates that potential at capacitor is not allowing the charges to move away from it immediately, implies capacitor won't allow instantaneous change in voltage. In this way, the potential across the capacitor will decay gradually, that slows down the charges moving away from the capacitor. It will continue until the potential across the capacitor becomes zero, and simultaneously, current will become zero. This process is known as discharging. Thus, during discharging time, capacitor acts as a voltage source. The time taken for the capacitor to completely discharge is called as discharging time of the capacitor. In this video, we have discussed how capacitor behaves in DC.